Now, example 7.2. A pure inductor of 25 millihenry is connected to a source of 220 volt. Find the inductive reactance and RMS current in the circuit if the frequency of the source is 50 hertz. Okay. Now see, inductance that is given to you 25 millihenry. So that is 25 into 10 raised to minus 3 henry. RMS voltage that is 220 volt, frequency that is 50 hertz. Now inductive reactance that is denoted by XL and that is equal to omega L. But omega that is 2 pi F. So we can write the inductive reactance XL that is 2 pi FL. Now substitute the values 2 pi F 50 L 25 into 10 raised to minus 3, you will get XL. Now RMS current that is RMS voltage upon reactance. So V by XL 220 upon XL, whatever is the value of XL obtained here, substitute, you will get the answer. Clear to all of you? Then after example 7.3. A lamp is connected in series with a capacitor. Predict your observations for DC and AC connections. What happens in each case if the capacitance of the capacitor is reduced? Now, capacitance that is C, and how the capacitive reactance depends on C. So Xc equal to 1 upon omega C. So here as the C increases, Xc decreases. As the C decreases, Xc increases. Now equation of the current I that is V by Xc. Okay. So Xc that is 1 upon omega C. So you can rewrite this one I that is V omega C. If C is decreased, then Xc will increases. So if Xc increases, then I will decrease and brightness of the bulb decreases. But if it is connected with DC, then to DC, resistance offered by capacitor that is infinite, because for DC, the frequency is 0 here. So if capacitive reactance is infinite, then current will be 0. So simply we can write with DC, current will be 0. Simple thing. Example 7.4. A 15 microfarad capacitor is connected to a 220 volt 50 hertz source. Find the capacitive reactance and the current RMS and peak in the circuit. If the frequency is doubled, what happens to the capacitive reactance and the current? Now see, capacitor that is with capacitance 50 microfarad, that is 15 into 10 raised to minus 6 farad. RMS voltage that is 220 volt, frequency that is 50 hertz. Now capacitive reactance Xc that is 1 upon omega C. So we can write that is 1 upon 2 pi Fc. Now here if we substitute F and C and then solve it, we will get here Xc. Now RMS current. So RMS current that is RMS voltage upon Xc. RMS voltage that is 220. And then substitute the value of Xc here. Now you will get RMS current. So now peak current that is RMS current into root 2. So RMS current we calculated here, multiply it by root 2, you will get peak current, or we can say maximum current. Now if a frequency is doubled, then what happened to the capacitive reactance and current? Now see this equation. If frequency is doubled, then capacitive reactance will be half. And if this capacitive reactance becomes half, then the current will be doubled one. Clear to all of you? Any doubt in this one? Now next theory, that is AC voltage applied to series LCR circuit. Now when inductor, capacitor and resistor, all these three are connected in series with AC source, then what will be the current in the circuit? That we have to find. Now here we can do this thing by two methods. One, that is the phasor method, another one, that is the analytical method. So both the method that we have to discuss here. Now see, supply voltage V, that is Vm sin omega t. Now suppose at a particular instant t, the charge on the capacitor is Q and current in the circuit, that is I. Then we can write the potential drop across inductor, that is I dL by dt, across capacitor, that is Q by C, across resistor, that is IR. So as per Kirchhoff's second rule, the summation of the potential drops across these components, that is equal to the supply voltage. So L di by dt plus Ri plus Q by C, that is Vm sin omega t. Clear? Okay. Now, first let's derive the equation for current with the help of phasor method. Now, when we take the phasor method, now we know this thing. When inductor, capacitor, resistor are connected with AC source or AC supply, then there is some phase difference between voltage and current in the circuit. And in individual circuits, we already discussed this thing. Okay. So in phasor diagram, either we have to take the phasor of voltage first as a reference, and then after, with respect to it, we can represent current phasor, or we have to take current phasor as reference, and then we can represent voltage phasors with respect to it. Now in this particular circuit, what we have to do? So here, remember this point. Here, inductor, capacitor and resistor, all these three are in series, and we already studied this thing. In series combination, current through each component will be same one. યાદ છે થર્ડ ચેપ્ટરમાં ભણ્યા હતા આપણે રેજિસ્ટરના કોમ્બિનેશન્સ ભણ્યા ત્યારે, રાઈટ? સિરીઝ કોમ્બિનેશનમાં કરંટ સર્કિટનો સેમ હોય તો આ સર્કિટ માટે સ્પેસિફિકલી કરંટ ફેઝર જે છે ને, આપણે એને રેફરન્સ લેવાનો. Now see here, current phasor is represented here arbitrarily. Now we know this thing, when resistor is connected with AC supply, then there is no phase difference between voltage and current. So phasor of voltage for resistance R, that should be represented in the direction of I, and its magnitude, that is the maximum value of voltage across R, that is VRM. Now in case of inductor, we know this thing, current lag behind by voltage in phase equal to pi by 2. Or in other words, we can say voltage lead the current by pi by 2. એટલે જુઓ, અહીંયા આપણે કરંટના ફેઝર થી વોલ્ટેજ ઇન્ડક્ટર માટેના જે છે એનો ફેઝર 90 ડિગ્રી અહેડ આ ડાયરેક્શનમાં આપણે રિપ્રેઝન્ટ કર્યો. So this is the phasor of VL. and its magnitude, that is VLM. Then after, in case of capacitor, voltage lag behind in phase by current by pi by 2. એટલે VC એ આપણે કરંટ કરતા પાઈ બાય 2 જેટલો પાછળ જુઓ અહીંયા આગળ બતાવ્યો. This is phasor of the voltage across capacitor. Clear? અને એનો magnitude, that is VCM. Now this part is VCM, this part is VLM, so resultant in this particular direction, that is VCM minus VLM. This is VRM. It implies that the resultant value of the voltage that we can calculate using Pythagoras theorem, because these two are perpendicular and this is the resultant one. So resultant Vm square, that is Vrm square plus Vcm minus Vlm whole square. But Vrm, this is the maximum voltage across resistance, that is maximum current into resistance. Similarly, VLM, that is Im into XL, XL, that is the inductive reactance, and VCM, that is Im into XC, where XC, that is capacitive reactance. Now, Vm square equal to Im square R square plus VCM IMXC minus VLM IMXL whole square. So Vm square equal to, now here take Im common and take it outside this bracket, so you will get Im square, and then take Im square from both this one common. So Im square into R square plus XC minus XL whole square. So Vm, take square root on both the sides. Vm equal to Im into R square plus XC minus XL whole square. Under root છે raised to 1 by 2. Clear? Now Im equal to Vm upon under root R square plus XC minus XL whole square. Voltage upon something that is equal to current, then this something is obviously resistance. Now this denominator is represented by Z, where Z, that is under root R square plus XC minus XL whole square, and it is called impedance of the circuit. Impedance of the circuit means the effective resistance offered by this combination LCR to the circuit. એટલે આ બધા ભેગા થઈને સર્કિટને જે રેઝિસ્ટન્સ ઓફર કરે છે, that is the impedance of the circuit, and it is denoted by Z, and Z equal to under root R square plus XC minus XL whole square. Now we have the equation for current I, that is Im sin omega t plus phi. Im substitute karo here. So Vm sin omega t plus phi upon under root R square plus XC minus XL whole square. Clear? Now phi that we have to find. What is the phase difference here? So see. Now this is the current. This is the resultant voltage. And now suppose the angle between phasors of current and resultant voltage, that is phi. Then if we take here tan phi, then that is this opposite upon adjacent. So we can write tan phi, that is VCM minus VLM upon VRM. VCM is replaced by IMXC, VLM is replaced by IMXL, VRM is replaced by IMR. Now if we take Im common, then that will be cancelled. So tan phi, that is XC minus XL upon R. Therefore phi, that is tan inverse XC minus XL upon R. So with the help of this equation, one can find the phase difference also. Now see here, if XL is greater, sorry, XC is greater than XL, then phi will be positive. And in that particular case, the circuit is called capacitive circuit. And if XC is less than XL, then your phi will be -1. And circuit is called inductive circuit. Now, from this one, we can represent the impedance of the circuit with phasors also. હવે જો એનું પણ ગ્રાફિકલ પ્રેઝન્ટેશન થઈ શકશે, કારણ કે અહીંયા જો tan phi that is XC minus XL by R. હવે એકચ્યુઅલી આનું આ જ છે, પણ હવે ફરક આપણે એટલો છે ખાલી એમાં કે આપણે એવું કરીએ કે અહીંયા રેફરન્સ એ આપણે x એક્સિસ ઉપર લઈએ. બરોબર છે? તો જો x એક્સિસ ઉપર આપણે રેઝિસ્ટન્સ R લીધો, તો XC y એક્સિસ ઉપર આવશે અને XL નેગેટિવ y ઉપર. રિઝલ્ટન્ટલી XC માઇનસ XL આપણે આટલું બતાવી શકીએ. સ્કેલિંગ આર્બિટરી લેવાનું છે. હા, so this angle is phi. So resultant Z, that is nothing but under root R square plus XC minus XL whole square. તો આ satisfy થઈ જાય. Clear? And tan phi, that is XC minus XL by R. તો impedance of the circuit જે છે એનું તમે graphical presentation આવી રીતે બતાવી શકો. Clear to all of you or any doubt in? Now analytical method to derive the equation of the current for LCR series AC circuit. Now, as per Kirchhoff's second rule, we can write L di by dt plus IR plus Q by C, that is equal to Vm sin omega t. But current I, that is dq by dt. So we can write here, if we substitute I, that is equal to dq by dt, then L d2q by dt2 plus R dq by dt plus Q by C equal to Vm sin omega t. Now see, the form of this particular differential equation is exactly like the differential equation of forced oscillations. તમને યાદ હોય તો આપણે સ્ટાન્ડર્ડ 11th ની અંદર ઓસિલેશન્સ ના ચેપ્ટરમાં forced oscillations ભણ્યા હતા, અને forced oscillations માટે આ ટાઈપનું ડિફરન્શિયલ ઇક્વેશન આવતું હતું આપણે. તો ઓબ્વિયસ છે કે એનું જે સોલ્યુશન આવતું હતું સેમ એ ટાઈપનું સોલ્યુશન આનું પણ આવે. એમાં આપણે વેરિયેબલ એ ડિસ્પ્લેસમેન્ટ y લેતા હતા અને સોલ્યુશન હતું y ઇક્વલ ટુ a sin omega t plus phi. તો અહીંયા વેરિયેબલ જે છે, બરોબર છે, આપણો q છે, q કન્ટિન્યુઅસ બદલાય છે, રાઈટ? અને એ સોલ્યુશનમાં કેપિટલ A જે આપણે લેતા હતા, that is amplitude. Amplitude means maximum value of displacement. તો અહીંયા આપણે solution of this equation લખીએ તો q equal to maximum value of q, qm sin omega t plus theta લીધું અહીંયા. So we can write the solution of this differential equation, that is q equal to qm sin omega t plus theta. Now differentiate this one with respect to time t. So dq by dt, that is qm, differentiation of sine is cosine, and of omega t plus theta, that is omega. So resultantly we are getting qm omega cos omega t plus theta. Again differentiate this one. So d2q by dt2, that is minus qm omega square sine omega t plus theta. Differentiation of cos, that is minus sine, and of omega t plus theta, that is again omega. So omega into omega, omega square. Now substitute these three values of q, dq by dt and d2q by dt2 in this particular equation. Clear? Now say L into d2q by dt2. So that is minus qm omega square sine omega t plus theta. Okay? Plus R into dq by dt. But dq by dt, that is qm omega cos omega t plus theta, is substituted here. Then q by c. So 1 upon c into equation of q, that is qm sine omega t plus theta. And that is equal to Vm sine omega t. Now, from these three, we can take Qm into omega common. So Qm into omega, this L is taken with this one. So omega square, 1 omega is taken outside the bracket. So minus omega L sine omega t plus theta. Plus R cos omega t plus theta, qm omega is taken outside the bracket. Here qm omega is not there, so we have to divide here by omega. So 1 upon omega c sine omega t plus theta. Now rewrite this one and rearrange the terms. R cos omega t plus theta is written first. Then after, from remaining two terms, sine omega t plus theta is taken common. So we can write 1 upon omega c minus omega L into sine omega t plus theta, and that is equal to Vm sine omega t. Now, for this particular left-hand side, multiply and divide by z. So here, multiplied by z, so qm omega z, divide by z. So r by z cos omega t plus theta, and here 1 upon omega c, that is xc, and omega L, that is xl. So we can write xc minus xl divided by z sine omega t plus theta, and that is equal to Vm sine omega t. Now qm omega z. Now this r by z, see here. From this one we can write r by z, that will be cos 5, because cos 5, that is adjacent upon hypotenuse. Sin 5, that is opposite upon hypotenuse, so xc minus xl by z. It implies that. Now r by z, that we can replace by cos 5, and xc minus xl by z, that we can replace by sin 5. Remaining terms are as it is. Then qm omega z. Now this one is cos A cos B plus sin A sin B. So for that we can write cos omega t plus theta minus phi. That is equal to Vm sin omega t. Now from this equation we can write Vm, that is equal to Qm omega z. If we take z on left hand side, then Vm by z will give you Im. So Im, that is Qm omega. And now cos omega t plus theta minus 5, that is sin omega t. That is possible only if this theta minus 5, that is minus pi by 2. Because cos omega t minus pi by 2, that is sin omega t. So we can write theta minus phi, that is minus pi by 2. Therefore, theta equal to phi minus pi by 2. Now, we have equation I, that is dq by dt, that is qm omega cos omega t plus theta. Now here substitute the value of theta, that is phi minus pi by 2. So I that is equal to Qm omega cos omega t plus phi minus pi by 2. But this one is nothing but sine omega t plus phi. So I equal to Im sine omega t plus phi, the equation of the current. And Im that is Vm by mod z. So that is under root r square plus xc minus xl whole square. And phi that is tan inverse xc minus xl by r. So this one is the equation of current by analytical method. In standard 11th, in chapter number 14 of oscillations, when we discussed forced oscillations, at that time we discussed this phenomenon of resonance. When the external driving frequency and the natural frequency of the oscillator becomes equal, at that time oscillator oscillate with maximum amplitude. તો હવે અહીંયા આગળ ઓસિલેશન્સ શેના થાય છે આ સર્કિટમાં? તો ચાર્જના ઓસિલેશન્સ થાય છે અથવા તો કરંટ increasing decreasing છે. તો આપણે એવું કહી શકીએ કે oscillating alternatively changing current છે. તો external driving frequency અહીંયા કઈ થાય? So that is the frequency of AC source. અને frequency of the circuit is same થઈ જાય. At that time resonance takes place in the circuit and the current in the circuit that becomes maximum, that is the resonance. Okay, now see, we have the equation of current I, that is Im sine omega t plus 5. In that Im, that maximum current, that is Vm upon under root r square plus xc minus xl whole square. Now xc that is 1 upon omega c minus omega l. Clear? Now see here, suppose we change the frequency, then if a frequency of the supply voltage is continuously changing, this current will also change. If we draw the graph of Im versus omega, then the graph that will be as shown in this figure. And this particular graph, that is called resonance curve. And see here, experimentally we can obtain this particular graph of Im versus omega. Now here, see, we are getting Im, that is maximum one for a particular frequency, right? Now see, from this equation you can understand this thing when this happens. See here, suppose for a particular value of the frequency, and say that particular value is omega 0. So for omega equal to omega 0, this xc that is equal to xl. So if xc and xl becomes equal, then this part will be cancelled. It implies that the denominator that will be minimum 1. So in that case, your Im that will be Im maximum, and that is Vm by R. And when this happens, then we can say the resonance takes place in the circuit. Or we can say this phenomenon of being Im maximum in the circuit, that is called resonance. Means when omega that is equal to omega 0, at that time, for that particular value of angular frequency, xc equal to xl. But xl that is omega l. So for omega equal to omega 0, we can write that is omega 0 l. And xc that is 1 upon omega 0 c. So omega 0 square that is 1 upon lc. So omega 0 that is 1 upon root lc. Clear? So when the frequency that is equal to 1 upon root LC, at that time, this phenomenon of resonance takes place. So this frequency that is called resonant angular frequency. That is called resonant angular frequency. And simply here you can write 2 pi f0 also, and f0 that is 1 upon 2 pi root LC. So that is called resonant frequency. Simple. Clear to all of you? Any doubt in this one?
સર આ ખબર ના પડી. આ સપોઝ ફોર ઓમેગા ઇઝ ઇક્વલ્સ ટુ ત્યાંથી.
સી અહીંયા તમે આ ઓમેગાની વેલ્યુ ચેન્જ કરો. માનો કે તમે આ ઓમેગા ઇન્ક્રીઝ કરતા જાઓ તો આની વેલ્યુ ડિક્રીઝ થતી જાય, આની વેલ્યુ ઇન્ક્રીઝ થતી જાય. તો મેથેમેટિકલી એવું થવાના ચાન્સીસ ખરા કે નહીં? આ બંને ક્યારેક એક થઈ જાય. તો આ બંને જ્યારે સેમ થઈ જાય તો આ પોર્શન 0 થઈ જાય. તો તમારો ડિનોમિનેટર મિનિમમ થાય, તો તમારો આન્સર અહીંયા મેક્સિમમ થઈ જાય. હવે આ કઈ વેલ્યુ માટે થશે આપણને નથી ખબર, એટલે આ તો મેં ખાલી ઓમેગા 0 એવું લખ્યું. તમારે ઓમેગા ડેશ લખવું હોય તો લખાય, એમાં શું. અને રેઝોનન્ટ ફ્રીક્વન્સી છે એટલે એને ઓમેગા સફિક્સમાં આર લખવું હોય તો લખાય. જે નોટેશન આપવું હોય આપો. ઓમેગા 0 આપો, ઓમેગા ડેશ આપો, ઓમેગા આર આપો, પણ ટેક્સ્ટમાં આ લખ્યું છે એટલે આપણે આ લીધું. ઓમેગાની કઈ વેલ્યુ ખબર નથી, એટલે માનો કે ફોર ઓમેગા 0 આવું બને છે, XC ઇક્વલ ટુ XL થાય છે. બરોબર છે? એ આપણે સપોઝિશન કર્યું. ચલો, ક્લિયર એકદમ? સો હિયર Im maximum associated with this peak of the resonant curve, that is for angular frequency omega equal to omega 0. Now see here, we have to first take half power bandwidth. Half power bandwidth, that is 2 delta omega. 2 delta omega, that is called half power bandwidth. And half power bandwidth means what? Okay, see, here, Pm, that is Im square into Z. બરોબર છે? Now for omega equal to omega 0, Im that becomes maximum, so that is Im maximum, and Z becomes R, because XL that is equal to XC એટલે cancel થઈ જાય. એટલે હવે Pm maximum, that is equal to Im maximum whole square into R. હવે બંને સાઈડ 2 થી ડિવાઈડ કરી દો તમે, તો Pm maximum by 2, that is equal to Im maximum into R square by 2. પણ હવે રાઈટ સાઈડ જે છે ને એને આપણે Im maximum by √2 whole square એવું લખવું હોય તો લખી શકીએ કે નહીં? ક્લિયર? તો આનો મીનિંગ એ થયો કે when our current is Im maximum by √2, at that time power is half. At that time power is half. Clear to all of you? So here we discussed this thing, when our current, that is Im maximum by √2, at that time the power is half. Now see, this one is our Im maximum value. Now multiply it by 1 upon √2, and suppose we get this particular point that is associated with Im maximum by √2. Now from this particular value of the Im, draw a parallel line to x-axis. It intersect graph at 2 points. Now from these 2 points, draw normal on x-axis. So corresponding to this 1 point here, we will get one angular frequency. Say it is omega 2, and corresponding to this other point on the graph, we will get another angular frequency here. Say that is omega 1. And now with respect to omega 0, omega 1 and omega 2, both are with difference of delta omega. So this omega 1 minus omega 2, that is called half power bandwidth, because for this particular angular frequencies, we are getting the current that is I maximum by root 2, and corresponding to this current I maximum by root 2, we have half power in the circuit, and therefore this is called half power bandwidth. Clear to all of you? So this 2 delta omega, that is called half power bandwidth, because at that time the power is half in the circuit. Now sharpness of the resonance curve, that is represented by the ratio omega 0 to 2 delta omega, and this is called Q factor. This is called Q factor. If the value of Q factor, means this ratio omega 0 upon 2 delta omega, is large one, so omega 0 upon 2 delta omega will be large one only if this 2 delta omega is a small one. And if this one is a small, means this portion that will be close to each other. It implies that this peak will be sharp one. So this ratio omega 0 upon 2 delta omega, that represent the sharpness of resonance curve, and that is known as Q factor. Now we have the equation of current Im, that is Vm upon under root R square plus omega L minus 1 upon omega C whole square. Now we already discussed here on the graph, we can write omega 1, that is omega 0 plus delta omega, and omega 2, that is omega 0 minus delta omega. So we have omega 1, that is omega 0 plus delta omega, and omega 2, that is omega 0 minus delta omega, as well as we have omega 1 minus omega 2, that is 2 delta omega. Now, if we take omega that is equal to omega 1, તમે omega 2 લઈ શકો, આપણે omega 1 લઈએ. So if we take omega equal to omega 1, then your current Im, that is Im maximum by root 2. હમણાં જ મેં તમને બતાવ્યું કે એ વખતે power half હોય, and that correspond to the value of the current Im maximum by root 2. એટલે જો આપણે આ ઇક્વેશનમાં ઓમેગા ઇક્વલ ટુ ઓમેગા 1 લઈએ તો આપણો Im જે છે એ Im maximum by root 2 થઈ જાય. And now this Im maximum that we can replace by Vm by R, કારણ કે આપણો Z એ R છે હવે, બરોબર છે? So now we can write under root R square plus omega 1 L minus 1 upon omega 1 C whole square, that is R root 2. So R square plus omega 1 L minus 1 upon omega 1 C whole square, that is 2R square. Clear? So omega 1 L minus 1 upon omega 1 C whole square, that is equal to R square. So omega 1 L minus 1 upon omega 1 C, that is equal to R. Now replace omega 1 by omega 0 plus delta omega into L as it is minus 1 upon omega 0 plus delta omega into C, that is equal to R. Now here from this bracket take omega 0 common. So we can write omega 0 into L. So 1 plus, now here we can write delta omega upon omega 0. Similarly from this bracket take omega 0 common. C is there already outside the bracket. So omega 0 C into 1 plus delta omega by omega 0. But see here, we have 1 upon omega 0 C, that is omega 0 L. So omega 0 L into 1 plus delta omega upon omega 0, and this 1 by omega 0 C, this portion, that is replaced by omega 0 L. This part as it is 1 plus delta omega by omega 0, and that is equal to R. Now from these two terms on left hand side we can take omega 0 L common. So first bracket 1 plus delta omega by omega 0 minus this denominator that we write in numerator with power minus 1. Then as per binomial theorem, we can rewrite this second term, take minus 1 here in multiplication. So 1 minus delta omega by omega 0, and that is equal to R. So simplify 1 plus delta omega by omega 0 minus 1 plus delta omega by omega 0, that is equal to R. So this one is in bracket resultantly 2 delta omega by omega 0. This one is omega 0 L as it is, that is equal to R. Omega 0 cancelled. So 2 delta omega, that is equal to R by L. Now substitute this value. Q factor, that is omega 0 upon 2 delta omega, but 2 delta omega that we proved R by L. So we can write that is omega 0 L by R. But omega 0, that is 1 upon root LC. So Q, that is L by R, 1 upon root LC, but L upon root L, that will give you root L. So Q, that is equal to 1 upon R under root L by C. So here we can understand if R is more, Q factor will be less, and sharpness of resonance curve will be less. If R is a small one, then sharpness of resonance curve will be more because Q factor will be more. Sharpness of resonance curve means, see, અહીંયા આપણે આ બે કર્વ ડ્રો કર્યા. R1 is less than R2. એટલે જો રેઝિસ્ટન્સ નાનો હોય તો આ પીક જે આપણને મળે એ શાર્પ મળે, અને જો R મોટો હોય તો આ પીક જે છે એ થોડીક આપણને ફ્લેટન્ડ મળે આવી રીતે. એટલે આની શાર્પનેસ ઓછી કહેવાય, આની શાર્પનેસ વધારે કહેવાય. Clear to all of you?